So welcome back. We are going to now move to a new section of the course where, as you can see, the tables are back. And so it's going to be, again, about storing data in something that looks like tables. And so you can see we've already seen a lot. We have seen how to store data in the cloud. So we have now S3, we have HDFS, we have Azure Blob Storage. We saw very briefly how text can be encoded into bits, but most importantly, how we could encode the data in text. And here we saw XML and JSON, which are two kinds of syntaxes. And today, we are going to be one level above, where we are going to be back to looking at data models. And I will show you something that is massively used at companies like Google to store that kind of data, XML, JSON, and so on. And so the spirit of the intro was to show you that back then, if you go back to the 70s, the 80s, the 90s, everything was done on single machines. You had a database, it was monolithic, it was just one machine, one server, PostgreSQL, for example. The problem is that then in the beginning of the 2000s, we had so much data that we wanted to accumulate that it didn't fit anymore on a single machine. You needed more machines in order to fit it. And so one first idea that you might have, as I told you, you could scale up. You buy more expensive machines, and that fits again, right? But it only goes so far, because at some point it becomes too expensive. And so instead of scaling up, we can scale out, right? So we can now have more machines. And this is exactly what some engineers at Google and other companies started to do. They installed PostgreSQL or a database system on multiple machines in such a way that you could store the data redundantly and partition the data across machines. The problem is that these first prototypes looked a bit artificial and very costly to maintain, because they needed to implement everything by hand. How do you store the data on that machine or on that machine? How do you maintain replicas of the data on multiple machines? So the cost of that was just very high, and that wasn't practicable. So the idea of just installing PostgreSQL on many machines, that doesn't provide you with a long-term approach. And so the idea is that since we have introduced HDFS, which already gives us a file system on which we can store petabytes of data, why don't we use this file system HDFS, as the basis for storing our tables? That is exactly the big idea here. And so we are going to use HDFS in order to get a system that checks all boxes. And what I mean with boxes is high throughput, low latency. You can update the data, larger values, larger collections, and random access. You can see that none of the systems so far checks all these boxes, right? If you look closer, for example, in object stores, you don't have a low latency. It takes some time to get and put the objects. You cannot do finer grained updates in place. You have to upload and download entire objects. And you don't have random access. In a relational database management system like PostgreSQL, you don't have high throughput. It's limited. It's a single machine. And you're also limited in the size of the collection, because that cannot exceed one machine. Then you look at HDFS. Why don't we just store our data on HDFS, right? We could store XML and JSON in HDFS. But the problem is that we don't have low latency. As I told you, in HDFS, when you try to use it, it takes 1 or 2 seconds every time you want to enter a command to access HDFS. You cannot update the data in place with a fine-grained approach. The only thing you can do in HDFS is upload blocks, upload files, upload blocks, or download blocks, but you cannot update just specific bits in a block. That you cannot do, right? That would be random access rights. So that's limited. And key value stores, which are not part of this lecture, they are another technology that I cover in big data. They also don't check all the boxes. But I have good news for you, because what we are introducing this week checks all of these boxes. I'm going to show you a system that has high throughput, low latency, supports updates, supports larger values, including XML, JSON documents, supports larger collections, and has random access. Right? So it's like magic, and that's beautiful engineering work that has been done by the people who designed this system. I'm going, as usual, to split this lecture into two parts. In the first part, I will introduce to you the data model, which is the logical data model, easy to understand, you will see. And then I will show you how it is implemented. The internals of the system, you will see it's very complex. Take the time to drive you through this. It's the most complex lecture of the semester. If you survive this one, you survived all of them. But let's start with the logical data model. Who is ready? Right? Okay. Who is excited? I mean, we're checking all of these boxes, right? That sounds like impossible to do that, right? And yet. So the system that we are going to study was originally invented at Google, and it was called Big Table, because the goal is to store a table that doesn't fit on a single machine. So they called it Big Table. And the idea is that when you manipulate data at these scales, you want to store together what is accessed together, because then you only need to read just once the bunch of data that is in the same block. For example, you read the block and that's it, you have it all. You don't want your data to be spread all over the place and to have to read from multiple places and then join that data. But that shouldn't ring a bell because we've already seen that. That's the idea of normal forms, right? And denormalization. When you have data in normal forms, you have multiple tables that all do their own things. You have a table for customers, a table for products, and so on. And when you want to analyze your data, you have to join these tables, right? But the join, first, it's expensive. And second, you have to read from multiple places. Because if you want to join these two tables, you need to read from one place the table on the left and to read from the other place the table on the right. Okay? So this is the reason why we denormalize the data, right? We throw away the normal forms. I have told you already many times. So if we denormalize this, we get this. We just get a bigger table that might have redundant data, right? The data might be repeated, but it's just one table now. And now, since we only have one single table and everything is at the same place, right? So this is exactly what I mean with we need to store together what is accessed together. It's yet again this idea of denormalizing the data. Okay, so having said that, it means that contrary to PostgreSQL, where we are going to have multiple tables, in that case, we just look at one, typically, one table at a time. Now, that table, that looks like a table, right? It has one special column. That special column is called row ID. It's an identifier for the record or for the row. For example, 000 is the row ID of the first row, 002 is the ID of the second row, and so on. Okay, so you could see it as a key value model where the row ID is the key and the rest of the row is the value. Who agrees with that? Right? This is one way to see it. Now, you will see that this here that provides us a tabular storage for plenty of data, it's not as high level as PostgreSQL or SQL, right? So it's not as fancy. And this is why the row ID is just really, some binary data, right? So it's just a binary identifier. In that case, you see it's base 16, right? Base 16 is when we use all the digits from 0 to 9 plus the letters from A to F. That's base 16. So this is just a binary thing, the row ID. Then, what is special and a bit different from relational database management systems is that the columns are organized in families, right? We don't have just the columns, we have families. The justification for them, for example, you could think that this is when you used to have the tables in normal form and you denormalized, the column families correspond to what were the tables before you denormalized, right? You basically just keep track of which columns came from where. And that just basically allows them to nicely organize the columns in this way. So maybe the purple column family might have the products information, the yellow family might have the customer information, the red family might have all the products description in HTML and so on, right? Who is with me? Right? So this is new that we do not have in the relational model, this notion of column family. And then within a column family, you can give them names. So here I used, you can call them anything, right? Again, it's binary data. So I used Latin letters for the purple column family, Indo-Arabic numbers for the yellow family, and the Roman numbers for the red family, right? Just as an example. So you see that if you want to identify a column, you need two things. You need the column family plus the name of the column, right? The column family plus the name of the column. The color here plus the letter or digit. What is really nice when you have these column families is that you can create new column names within a family on the fly, just like that, in real time. So imagine you already have this table. It has 1 billion rows. It already has these 3 column families. You can create column C and columns 2, 3, 4 in Roman numerals, just like that in real time. All you need to do is insert a new record that uses column C and columns 2, 3, 4. And that's it. And it's instant. That is in sharp contrast with PostgreSQL, where you can add new columns. But it's going to take a while, because if you add a new column, it has to reorganize the disk layout completely to provide with this new column. Here, we can add new columns just like that, instantly, on the fly. For whom is that clear? Yeah? All right. So again, I insist here, everything is binary. We don't have the luxury of PostgreSQL where you have the integers, the decimals, the dates, the strings, and so on, all these types. Here, it's a lower level. Everything is just a bunch of zeros and ones. It's all binary. So the row IDs are binary. The column families and column names are binary, and so on. Everything is binary. But of course, what people typically do in practice is that they are going to put text in binary. So they use actual strings for the column names, and then these strings are just mapped to binary, right? But we don't have the luxury of fancy types like dates, integers, decimals, and so on that we don't have, right? Okay. Now, something more that is different from a typical relational database is the size of the cells. Every one of these cells in here that you see can have a size typically of up to 10 megabytes. In a relational database management system, you don't do that. In a cell, you just put one number or one small string, or but you don't put huge values, right? At least historically. But here, you can put values in the cells up to 10 megabytes, and it will just work. Now, what do we do with 10 megabytes? Well, for example, I could squeeze an entire JSON document, right? It can be a few megabytes. I can have a lot of JSON data in there. I could squeeze an XML document. I could squeeze an HTML page. And in fact, if you have a website where you generate the contents dynamically, you could put the HTML in a table like that, right? 10 megabytes is a lot of, it's a very high size, right, for squeezing some XML, JSON, or HTML. Who agrees? Right? So this is what makes it very, very nice. So it's not S3. You cannot go all the way to 5 terabytes and so on. But 10 megabytes is pretty nice. So now imagine you can have a table like this that has billions of rows, that has potentially thousands or millions of columns, and that has cells that can be up to 10 megabytes. It's absolutely monstrous, right? Gigantic, a table like that. Of course, if you have billions of rows and millions of columns, and the cells can be up to 10 megabytes, as you can imagine, not all the cells are filled. It's very sparse. You're going to have a lot of empty cells in there, right? A lot of unused column names in the rows. So this is the idea. Who is with me? Right? Any questions? so far? So this is the model. This is the way we look at the data. Next, I will tell you how we can query it, how we can access this data. Again, here, we do not have the luxury of PostgreSQL. We don't have a SQL language or a relational algebra or something. It's a bit simpler than that because it's really just a storage layer as a table. And we have 4 types of queries that we can do. And the first ones are not going to surprise you. The first one is get. You can get some data if you give some row ID. For example, I give you row ID 0A1, and I want to get the data for that row. That is the first thing that I can do. I can retrieve data from my big table. I can also retrieve data for some column families. If there's a lot of data on that row, I could say, I'm interested in the data for 0I1 just for the purple column family. So I could just ask to have just that. Or I could have the yellow and the red column families, right? You don't even have to get the entire row. You can select specific column families. So get is the first thing you can do. The second thing you can do is put. You can put some data. For example, let's put the data in 204 for also specific column families, purple, yellow, red. So let's do all of them here. So I put some data in place. It's like inserting data in the system. Do you see how it's actually close to S3? In S3, we could also get an object and put an object, right? So it's the same idea. You can get, you can put, except that it's more organized than S3, right? Here, we don't have just bucket IDs and object IDs. We have a 2-dimensional grid of objects, right? And these objects can be up to 10 megabytes. Okay. So get, put, can you guess the third one? You can guess it. Get, put, delete, yes, exactly. You can delete. Let me, oh, I had the scan in between. Delete, let me show delete since you said it. So you can indeed say, please delete the row that has this row ID, and it all goes away. Of course, you can also just delete a column family part of a row. That's also fine too, right? Delete. Okay, get, put, delete, and the fourth one, that is scan. Scan allows you to look at a bunch of data across multiple rows and multiple column families. Right? So you could say, scan everything between 000 and 4A2 for all column families. And then, so typically you do it in some programming language, right? But basically then that gives you a way, you receive the data and you can iterate through all of that to process that data. So this is a scan. You can also say, I want to scan between 000 and 4A2 only the yellow family, or you can say, I only want to scan between 1E0 and 22A, the yellow column family, right? So this is the scan. Okay. For the scan to work, there is an additional constraint on the row ID, is that it is sorted, right? The rows are sorted by row ID. You can see 000, 002, 0A1, A1, it's nicely sorted. So Bigtable maintains a sort on this. Okay. Get, put, delete, scan. Just these 4. We don't have SQL or any fancy language, at least not yet. Now, about the terminology, because the name of the lecture was white column store. So I need to make sure that we get the terminology correct. I told you it's a key value model. So key value model is something very generic whenever you have the structure of a key associated with a value. We saw the key value model plenty of times already in that lecture. We saw it in S3. The key is the bucket ID plus the object ID, right? And the value is the object. We saw it in Azure Blob Storage, where instead of a bucket ID and object ID, they have 3 components of a key, but it's still the same idea, right? We saw the key value model in JSON objects, right? A JSON object has key value pairs. We also saw the key value model in XML attributes. Do you remember the XML attributes? The attribute names cannot repeat. We also have keys there. So this is the key value model. And we saw it again in Bigtable with the row ID that is the key and the rest of the row that is a value. So this is what key value means. It's very, very generic. Then there is something that we call column storage or column-oriented storage. This was also quite a hype 15 years ago. Yes, we have a question.
Do we have something like an ad, or is it simply that I put with a new ID is like an ad?
An ad? How do you spell it? A-double-T. Addition. In the language. Yes, so indeed, this is what I meant with we don't have the luxury of SQL. That's exactly what I mean. We do not have add, multiplication, or any fancy operations. We can only get data, put data, delete data, and scan data. If you want to add or do fancy things, you need to do it in a programming language outside of this system, right? In the programming language.
Oh, no, he says in the sense to add a new row, but yeah, that is a put indeed.
Oh, to add a new row. Oh, yes, yes. Sorry, I misunderstood. So yes, that's what put does. Put is able to add a new
I also misunderstood, I'm sorry.
No worries. So put can either replace an existing row or it can add a new row, absolutely. Just like in S3, when you do put in S3, that can create a new object for a key that didn't exist, or that can overwrite an object for a key that existed.
Thank you.
Yeah, thank you. All right. Very good. So column-oriented storage. For those of you who visited Information Systems for Engineers, you might remember that PostgreSQL stores the data on disk of the tables, and it does that in a row fashion, meaning that if you look at the content of disk, you will see one row and then another row and then another row and then another row, right? So the contents of one row are together. Column-oriented storage was a change of paradigm that you still have tables, but if you look at the way they are stored on disk, they are stored by columns. So on disk, you will have this entire column, and then this entire column, and then this entire column. The data is the same. Logically, it's still a table. It's just the way that it is stored on disk that is different. And the reason why people started doing that is that if you have large tables, then having the columns stored together means that if there is imagine that there is 100 columns in your table, and you have a query that only needs to access 2 or 3 of them. Then if the colors are stored together on the disk, you just need to read these 2 or 3 columns, and you ignore all of the other columns. But do you see that if the data were stored in rows instead, that forces you to read everything, right? Because the rows are together. Right. So this is why storing in columns can be a performance improvement for the queries that only use specific columns. Who understands that? Yeah, very good. And now when we say wide column stores, the wide is this idea that unlike a traditional relational management database management system where you can have up to 250 rows, roughly, in a wide column store, you can have thousands, millions of rows, of columns, sorry, I mean columns. You can have up to 250 columns in a relational database management system and up to thousands or millions of columns in a wide column store. That's why it's called wide. And to make it work, we need to organize the columns in column families. And it is the column families that we are going to store together. Who is with me? Repeating, okay. Now, Bigtable is the original product. HBase was the open source version of Bigtable. And in fact, I'm going to focus on HBase in this course. That's the one that is fully public, proprietary, and that is the one that is integrated with HDFS. So the H here stands for Hadoop, just like the H of HDFS stands for Hadoop. Cassandra is the Facebook or Meta version of a wide column store. It's a bit different, but that I'm not going to focus on it. But if at some point you need to learn Cassandra, then you'll have no difficulty doing that because you will know HBase, right? Okay. Any questions on the logical data model? No questions? All right. So I recap. We have very big tables that can have billions of rows and millions of columns. Every row is identified with a row ID. A column is identified with a column family plus a column name. The cells can be up to 10 megabytes each, but it's very sparse. Okay? So now I'm getting to the very, very scary part. That is the one that where the complexity is going to start. Yes, go ahead. Yes, absolutely. So first, there is something you could do is you could go and change the configuration to allow for more than 10 megabytes because it lets you. So you can change to allow for more, but then it might get slow or start breaking. And indeed, what you can then do is split it up over multiple values and store it in different cells. Or maybe you should not be using HBase. Maybe then you should be using HDFS. And so if you want to store a gigabyte of data, maybe you can directly pour it in HDFS without HBase, right? So HBase is great when you have a lot of medium-sized XML, JSON documents, HTML documents, and so on. Right? Does it answer your question? Awesome. Who is ready for the scary part? Okay. I'm only going to scare you for 10 minutes though, because it will be next week that we'll get into it. But I'll try to take it slowly. So this is my data model. I have my row IDs, my column families. Do you remember that when we stored the files in HDFS, we split the files. We split them into what? Blocks, yes, exactly. We split them into blocks. We are also going to split in here because that's too big. There are billions of rows and millions of columns. And we are going to split it like a wedding cake, meaning horizontally and vertically. The horizontal splitting is what we call regions. A region is an interval of row IDs. Remember that the row IDs are sorted, right? They are sorted ascending. So all I need to specify a region is the minimum and the maximum of my region. Now, just because for the beauty of it, we take the minimum included and the maximum excluded of a region, meaning that if I say a region between 1 and 5, it's going to be 1, 2, 3, 4, right? Starting at 1, but excluding 5. The only reason is just for elegance. The only reason is that the max exclusive will be the min inclusive of the next region. That's the only reason, right? Okay, so this is a region. That is my horizontal splitting, horizontal partitioning, okay? And then I'm also going to split vertically. And here I don't have to think a lot. I'm just going to take the column families. And if I take now this slice of my wedding cake, so the intersection of a region and a column family, I get this one unit that would be the unit of storage, of partition, of HBase. Okay, so this is what we store together. And we are going to look closer at how a specific region and column family are going to be stored on top of HDFS and in the memory. All right, so this is the first thing to remember. Now, we are going to need machines. Just like for HDFS, we had the name nodes and the data nodes. We are going to need a lot of machines, thousands of machines. Well, I have very good news for you is that the architecture and the way we connect the machines is going to be exactly the same one as for HDFS. Remember HDFS? We have the name node, we have the data nodes. The data nodes store the blocks, and the name node is kind of the brain, so has all the metadata. Well, for HBase, I just need to give them different names, but that's pretty much it. It's the same thing. So the coordinator node is called an HMaster, and the worker nodes are called the region servers. Do you remember that I told you that when we say here the name node is a machine and the data nodes are machines, these are not really machines. These are processes running on a machine. right? Just like on your computer, if you do Alt-Tab, you see you can go, there's Excel, Word, the mail client, the browser, and so on, so you can switch between your applications, right? These are processes on your machine. The name node is a process that runs on that machine, and the data nodes are processes that run on each one of the machines. And so what we have here is that the HMaster is also going to be a process that runs typically on the same machine as the name node, the same physical machine. We have a name node process and the HMaster. If somebody would log on to that machine, and imagine it has a fancy operating system, typically has Linux, and if you would press Alt-Tab, you would basically have name node and HMaster to switch between. And if you look at the other nodes, the worker nodes, they have a data node process and a region server process running on them. For whom is that clear? Right? And so very often people say the region server, the name node, the data node, the HMaster, as if it were the machine. But really, always remember, it's a process running on the machine. Okay. So now let's look at the HMaster. It's very similar to HDFS. You remember that for HDFS, whenever you needed to do something with the cluster, you needed to connect to the name node. The client needs to connect to the name node to create a directory, to delete a directory, to write a file, read a file, and so on. It's the same thing here. If the client wants to create a new table or delete a table and so on, they need to connect to the HMaster, right? So these are called the data definition language, DDL operations. Okay? You can create a table or you can delete a table. Now, I told you that we have this partitioning, this horizontal partitioning into regions. This is decided by the HMaster. So the HMaster is going to decide which region is assigned to which region server. For example, here we can see that it decided that this region server over here is responsible for this region and this region. This one over here for these two regions. This one over here is responsible for this and these regions, and this one over here is responsible for that region. Now imagine with thousands of nodes, right? But that's the idea. Who gets it? Right? So this is an assignment of responsibility. It's a duty. They are all on duty and responsible for specific regions. Now, a region can grow because if people use put a lot, and imagine that somebody starts putting a lot of data in the blue region, gigabytes of data, terabytes of data, all in the blue region. At some point, that region is going to grow too big, right? So what do? We split it. That's going to be done by the region server who is in charge of the blue region. They will notice that the region is too big and they will spontaneously split it. So they decide on some bound in the middle and they split it into regions. What's going to happen after it has been split is that that same region server that split the region might be overloaded, has too many regions to take care of. Yes, we have a question.
A region is a range of rows or a range of rows and column families?
It's a range of rows. So let me make that very clear. This is a region. A region is a range of rows across all column families. That is a region. And later, when we will look at the storage on disk, we will look at an intersection of a region and a column family, right? But a region is a range of rows. That's all it is. So this is why there's no column families shown on this, because when I say that a region server is responsible for the blue region, it means it's responsible for all column families in that blue region, all of them, right? Okay. So now we split, and what's going to happen is that this region server has too much to do. It has too many regions that it's responsible for. What do you think we are going to do? Exactly. We just change the responsibility. For example, the HMaster might say, from now on, you are no longer responsible for the yellow region. This is transferred, the responsibility of it is transferred to this other node. Okay? And again, it's only a responsibility that is transferred because, as we will see, and I'll take it from there next week, the data is stored in HDFS, the actual data. We will see how, but it's stored in HDFS. So this is why I insist, this is the responsibility of a region that is transferred. We don't move the data. The data is still safe on HDFS. Okay, so I'm going to stop here. Who was scared so far of the physical implementation? Not too scary, right? I will show you next week more details of this. All right, so thank you very much for coming to the lecture. Thank you, Ludovica, for the moderation. Thank you for all the questions. If you have anything you need to ask, then tell us. You know, there is the forum where you can ask questions. You can send us emails. You should read the big data textbook. I wrote it extra for you so that you can read it on your own time and at your own pace. Yes?
The question about the table's name from before, I answered, and I said normally the convention says to have an element with the plural name as an outer layer and then having singular name. And then I received another question with, so it does not get its own attribute, which I don't really understand.
So indeed, I agree with the answer that you gave. Maybe for the attribute, can you write us an email with the details of your question? We can take it from there.
Yeah, okay,
right?
Thank you.
And
or write it on Moodle, that's also okay.
Or on Moodle is also okay. Yes, absolutely, we will answer. All right. So thank you for attending today's lecture. Thank you for bearing with me with the new setup that, as you can see, still requires a bit of work, but after a while, we'll get used to it. And enjoy the exercise session. I'll see you next week at 8 a.m. for the continuation of this lecture. Thank you very much.